Hey everybody, welcome to the Photochemical Isomerization lab. Here's the outline for this video. I'll be going over the reaction, and the lecture portion might take a little bit longer because there are a lot of new techniques that I want to cover, like thin layer chromatography, the recrystallization technique, how to take melting points, and the neutral mold technique. But then I'll show the experiment in the lab in the end. Here's the reaction that we'll be doing. We'll be taking trans 1,2-dibenzoyl ethylene and forming the cis isomer of that molecule using visible light to progress the reaction. And that's why this lab is called Photochemical Isomerization, because photochemistry is the study of chemistry done with light. So we'll actually be leaving the reagent in a solution by the window for multiple days to allow this reaction to happen. Now let's briefly talk about what's going to be happening. If we look at the reagent, the highest occupied molecular orbital would be the pi bond, and that's where the valence electrons will be. But to convert it into the cis isomer, there would need to be rotation around those two center carbons, but the pi bond won't allow it. Double bonds don't rotate unless enough energy is provided, and that's where the light comes in. Light will come in through the window and be absorbed by the electrons in the pi bond. As one of those electrons absorbs a photon, it'll get excited and jump up into the antibonding orbital, which has an additional node, so this will weaken the pi bond, allowing for rotation. Eventually, the excited electron will relax and the cis isomer will be formed. So, visible light causes the reaction to happen. And now you might be thinking, well, wouldn't it also be able to just reverse the reaction then? Couldn't it react with the electrons in the pi bond of the cis isomer, exciting an electron to isomerize it back into the trans isomer? But that actually doesn't happen because of the shape of the product and how that shape affects the energy levels of the molecular orbitals. The reagent is completely planar, all the carbons are sp2 hybridized, but if we look at the product, these two oxygens do not want to be this close to each other, and they actually start to repel each other, kind of bending the pi bond in the middle, making this molecule non-planar. That non-planar conformation changes the energy levels of the HOMO and the LUMO, so that visible light no longer offers enough energy to reverse the reaction. Light with a higher energy or a higher frequency would be able to reverse this reaction. So for example, UV light would be able to do this, but the windows that we're placing the solution next to absorb UV light, so we won't run into this issue. That means that given enough time, the trans isomer should be mostly reacted, and we should be left with mainly the cis isomer. We'll also see the solution turn from a yellow color to more of a clear color as the reaction progresses, because the trans isomer, since it absorbs visible light, is a yellow color, whereas the cis isomer is clear since it does not absorb visible light. We can monitor that this reaction is happening over multiple days or multiple lab periods using thin layer chromatography, which is a way to separate compounds based on their polarity. And here's kind of how that works. We take an aluminum foil sheet, or even glass or plastic, and coat it with silica gel, which is a polar compound that looks something like this. And out of the two compounds that we're dealing with, the cis isomer will be more polar since the two oxygens are on the same side of the molecule, meaning that it'll interact more with the silica gel than the trans isomer will. So this is what we'll do. We'll spot the TLC plate with the reaction solution, and the solvent will begin to evaporate, leaving the solid material on the silica gel. Then, after a few days of leaving the reaction solution by the window, we'll spot the TLC plate a second time, and after a few more days, we'll spot the TLC plate a third time. You actually might end up doing this more than 3 times, depending on what the schedule says on the syllabus or what your instructor says, but the idea is that we'll spot a TLC plate multiple times to monitor the progression of the reaction. Once that's done though, we'll develop the TLC plate using methylene chloride as the mobile phase, and we can do that in the larger WMSC bottle in our drawers, taking off the lid and adding just enough methylene chloride to line the bottom of the bottle. Then the TLC plate can be added, making sure that the level of the methylene chloride doesn't go over where we spotted the product. Then the lid can be placed back on, and at this point the methylene chloride eluent will start to move up the TLC plate, and as it does so, it will dissolve the compounds that we spotted on the silica gel and move them along with it. Now, the speed at which these compounds move through the silica gel along with the eluent depends on how well they interact with the silica gel. More polar compounds will interact more with the silica gel and therefore will move slower up the TLC plate than less polar ones will. In this experiment, we actually won't really be able to see the spots as they move up the TLC plate, but the compounds are there and they are moving with the solvent. We'll allow that solvent to move up the TLC plate until it reaches close to the top. We don't want to allow it to run completely through the TLC plate, but just close. We can then take it out of the bottle and mark where the solvent reached on the TLC plate using a pencil. And while I'm talking about it, make sure that you mark everything on the silica gel with pencil because graphite won't mess up the separation, but the ink and pen can. Then we'll observe the TLC plate under a UV light so that we can see where the compounds ended up. Here, the top spot would be for the trans isomer. Since it is less polar, it wouldn't have interacted as much with the silica gel and would have moved farther than the cis isomer, meaning that the bottom spot would be for that cis isomer. And from this, we can see how the reaction progressed over time because the first spot that we made on the TLC plate contained a lot more reagent than product, but by the third spot, we're seeing a lot more product than reagent now. We'll want to mark all these spots with a pencil so that even when we're not looking at it under a UV light, we can still see where everything ended up. And finally, we'll calculate the retention factor, which is done by taking the distance the compound traveled and dividing it by the distance that the eluent traveled. So it's just a ratio. If we did this for the trans isomer, it looks like it traveled about half the distance that the eluent traveled, so the retention factor would be 0.5. And we're just going to eyeball this. We don't necessarily need to get a ruler out and measure all of the distances because the retention factor isn't standard. It can drastically change depending on the eluent used. To start this whole reaction, we'll dissolve the trans isomer in some ethanol using a hot water bath to increase the solubility of the reagent in that ethanol. Then, once it's fully dissolved, we'll spot a TLC plate with that solution to monitor the reaction, like I just went over. And then we'll spot a separate TLC plate for a group exercise. And in this exercise, we'll be testing how the polarity of different solvents affects the retention factor. So this will be done in groups of 4. 4 students will spot their own TLC plates with their own reaction solution, and then each student will develop their TLC plate with a different solvent, one of these 4. We can see that the polarity of these solvents increases as we go down the list. So the whole point of this exercise is to see how these different solvents affect the movement of an identical compound through the silica gel on a TLC plate. Once those have all been spotted, you'll want to cover your test tube with some parafilm and label it with your name and section number so you know which one is yours, and then place it in a rack by the window designated for your section. We'll allow that reaction to happen in the window, spotting the initial TLC plate again in future labs. With some time, the product will actually start to crystallize out of the ethanol solution, so we'll separate it from the ethanol using vacuum filtration. And to do that, we'll be using a Hirsch funnel, which looks like this. At the top, we have the funnel with a neoprene stopper inside attached to a filter flask, and this is where we'll be pouring the solution. All of the tubing is connected to a vacuum, so when we turn on that valve, the ethanol will be pulled through the funnel, and the solid product will be gathered on top of the neoprene stopper inside the funnel. We'll let those crystals stay on top of the funnel for a little while so that the vacuum can pull all of the ethanol through and make sure that they're nice and dry. The product can then be removed, and we'll check the purity of those crystals using another TLC plate. To do that, we'll take some and dissolve it in methylene chloride and spot the TLC plate with that product solution. And we'll also spot it with a standard solution so that we have something to compare it to. In this case, we could even use the reagent as a standard. So we'll take a TLC plate, spot it with the product and with the standard reagent, and then develop the TLC plate using methylene chloride. And it might end up looking something like this, where the standard is mainly the trans isomer, because that's the reagent, but there could also be some cis isomer there, because it might have already started reacting. But on the product, in this example, this would be a pure product because it only contains the cis isomer. If this is how our TLC plate turned out, then we could actually move directly on to characterizing the product since it would be pure. But if it was impure, then this is how the TLC plate would look. We would still have mainly the cis isomer, but above is a second dot, which would be for the trans isomer contaminating the product. If this is how it turns out, then we'll want to purify the product before characterizing it. To do that, we'll use the recrystallization technique by dissolving the solid in a minimal amount of solvent, and to make sure that it is minimal, we'll be doing that in a hot water bath. Then we can allow the solid to crystallize out of that solution slowly. Coming out too quickly can create an impure crystal structure because impurities will get trapped within that structure, but a slow recrystallization forms pure crystals because those impurities are allowed to escape before the crystal structure fully forms. Once that's done, we'll separate the crystals from that solution by either doing vacuum filtration again or using a centrifuge, which is actually what I'm going to be showing in the lab. I'm going to walk through this using some diagrams because this is a technique that we're going to use a lot in future labs, and it seems to be a technique that students tend to struggle with. So here we go. Here's the hot water bath. We'll take the product and place that into a test tube or a Craig tube and then put that into the water. Then we can place the solvent that we'll be using to dissolve the product into a separate test tube and put that in the hot water bath as well so it can start heating up. And in this lab, we'll be using 95% ethanol as that solvent. From here, we can start adding the solvent to the product, and as we do so, it'll start to dissolve, but we want to be really careful to add the solvent slowly. If too much is added, then the product could have problems coming out of solution even when we cool it down. So we'll continue to add the ethanol slowly, stirring the solution as well, just up until the product is fully dissolved. Once there, we can transfer it to an ice bath to check that the product can come out of solution. Usually what happens is it crashes pretty quickly out of solution, which is not what we want. We want a slow recrystallization. But at least we know that we can get the product back. So what we'll do now is transfer it back to the hot water bath, redissolving the product fully in the solution, and then this time leave it at room temperature so that the product can come out of that solution slowly, forming nice crystals that we can characterize. To characterize the product, we'll take its melting point and also run an IR spec, this time using the neutral mold technique since the product is solid. And I'll show how to do both of those techniques. To take a melting point, we'll be using an open-closed capillary tube, which look like this. And like the name says, one of the ends is open and the other is closed. So what we'll do is take the open end of the tube and press it onto the crystals, kind of spinning it around to force the compound into the tube. Then we can flip that upside down and tap it onto the counter until all of the crystals are at the bottom of the closed end. And we don't need very much, 1 to 2 millimeters will be just perfect for taking the melting point range. Then we'll preset the melting point apparatus, which looks like this. We'll want to set the starting temperature a few degrees below the actual melting point, just in case there is contamination. So for our compound, which has a melting point of 134, usually 5 degrees lower is a good starting point, so we'll start at 129 degrees Celsius. Once that's ready, we can place the product into the apparatus, and it might be hard to see in this picture, but the capillary tubes are inserted here. Then we can slowly raise the temperature, looking through the microscope to see exactly when the solid melts. And we're not measuring an exact melting point per se, but we'll be recording the melting point range by recording the temperature where the crystals start melting and recording the temperature when they are completely done melting. As for the Nugel mold technique, Nugel is a brand of mineral oil used to suspend solid products between salt plates. So what we'll do is add a little bit of the product onto the salt plate, just a few crystals, and then add a small drop of the Nugel. Then we'll place the salt plates together and mold them together really well until the solid is left as a film in between them, shown in the bottom picture. Then the IR spec can be run like normal, and we'll analyze the peaks. But be aware that the mineral oil is composed of a bunch of alkane chains, so we're going to see larger peaks for the carbon-hydrogen bonds and for the carbon-carbon single bonds, even though our molecule might not have very many of these. Now, this spectra was run with just Nugel, but if too much Nugel is added compared to how much product is added to the salt plates, then we might see something like this, where we mainly only see the carbon-hydrogen and carbon-carbon bonds. So you might have to mess around with the ratios a little bit and mold the plates together for a little while until a spectra is created where all the pertinent peaks are clear enough to be analyzed. Alright, I'll start by weighing out 50 milligrams of the trans 1,2-dibenzoyl ethylene, and you can see its yellow color here. So I'll take that and add it to a test tube, and then I'll get 4 milliliters of 95% ethanol to start dissolving the solid. Once that's all been added, I'll put the test tube into a hot water bath and begin stirring the solid until it's completely dissolved in the ethanol. It might take some time as the solution heats up, but 4 milliliters is plenty of solvent and eventually it should completely dissolve. Now we're ready to spot a TLC plate with the solution. So this is what they look like. They come in this bottle, and what I'll do is mark on the TLC plate with a pencil where I'll be spotting it over the next few lab periods. And I'll also spot a second TLC plate for the group exercise. To create a small and accurate spot on the TLC plate, I'll be using this longer pasture pipette and extending it over a Bunsen burner so that there's a smaller surface area. Then I'll break off the end of it with my spatula, making sure to clean up any broken glass that would be left over. Now I'll dip that into the solution, which gathers just a little bit into the tip of that pipette, and as that's pressed onto the TLC plate, some of the solution will be left on the silica gel. I'll make a spot for the first day, as well as a spot on the second TLC plate for the group exercise. Once those have been spotted, I'll cover the test tube using some parafilm, so I'll cut off a square and then cut that in half because only half will be needed to cover it. The test tube can be taken out of the hot water bath and the parafilm placed on top of it. Then I'll put a label onto the test tube with my name and section number so that I know exactly which one is mine. I'll find the rack by the window that is labeled with my section number, then place my test tube in there and leave it until the next lab period. The TLC plate that will be used to monitor the reaction can be stored away in the drawer, and as for the other TLC plate, I'll be developing it using one of these solvents, and 3 other students will develop their own TLC plates using one of the other solvents. In this example, I'll be using hexane as the mobile phase, adding just enough to line the bottom of the bottle with that solvent. Then the TLC plate can be placed in, and I'll make sure to put on the lid so that the solvent doesn't evaporate as it moves up the TLC plate, which you can see happening here. Once the solvent gets close to the top of the plate, I'll remove it from the bottle and mark with a pencil how far the solvent traveled before it evaporates off the silica gel. Then, when observed under a UV light, the spot can be seen, and I'll mark that with a pencil so that when the UV light is removed, we can still see where the compound ended up. That can then be compared to the other TLC plates developed by the 3 other students, and it's pretty clear that the solvent used has a strong effect in how the exact same compound moves through the silica gel. After a few days, I can test how the reaction is going, so I'll grab the test tube, and you can see that the product has been coming out of solution in those crystals, but there's still quite a bit of yellow color, so there's probably a good amount of reagent still left over. Before spotting the TLC plate, I'll place the test tube back into a hot water bath and stir up the crystals to redissolve everything in the ethanol. Once everything is dissolved, I'll use a pipette again to make the second spot on the TLC plate. Then I'll recover the test tube with parafilm and place the label back on and put the test tube back in the rack by the window. On the final day, we can see where the reaction is at, and it looks like the crystals are a lot more clear this time, so that's a good sign that the product has been mostly formed. This time, before spotting the TLC plate, I'm not going to redissolve the crystals because I want to keep them, but I'll still make that third and final spot to see how the reaction has progressed. The test tube can be placed in ice just to make sure that all of the product has come out of solution, and while that's in there, I'll start setting up the Hirsch funnel. I'll place a large filter flask at the bottom to catch solvent in case too much is added, and I'll attach that to the lab vacuum using the vacuum tubing. And at the top, I'll clamp the small filter flask and attach it to the larger one with some additional vacuum tubing. The funnel with the neoprene stopper can be placed on top, and now we're ready to get going. So I'll go ahead and turn on the vacuum now, and we can see that it's working as this tube compresses. The product solution can then be run through, and you can see the ethanol being pulled into the flask while the product gathers on top of the filter. I'll rinse the test tube with some cold ethanol to remove as much product as possible, and I'll also rinse the crystals on the funnel with some additional cold ethanol. Then I'll just leave those crystals on there for a while until they're dry. While I'm waiting, I'll develop the TLC plate using methylene chloride as the mobile phase. And once it's done, I'll take it out and mark with a pencil how far the solvent traveled. Under the UV light, we can see that with time, less of the reagent was present, but it was still there on the third spot, which is probably why the solution was slightly yellow, even though the crystals looked pretty clear. Now I'll remove the dry crystals from the Hirsch funnel, and I'll test their purity by adding a little bit to a test tube and dissolving it in some methylene chloride. Then, using a Pasteur pipette, I'll spot a TLC plate with that product solution, and I'll also spot it with a standard solution of the reagent. Once that's developed, the product actually looks pretty pure. I'm only seeing one spot on the side of the product for the cis isomer, so I'm actually going to jump straight into characterizing the product, but I'll show the recrystallization technique at the end so you can still see how that's done. I'll weigh out the full watch glass with the product on it. And then in the back of the lab, I'll grab one of the open-closed capillary tubes so I can start taking a melting point. I'll press the open end of that tube onto the crystals while spinning it to get some product in the tip. And by tapping the tube on the counter, the product can be moved into the bottom of the closed end. And now I'm ready to set up the melting point machine, which looks like this. So to set it up, I'll set the starting temperature to 129 degrees Celsius, which is just a few degrees below its melting point. And the stop temperature is well above the melting point, so that's great. The ramp rate is 2 degrees per minute, which is also good, so I'll go ahead and press start so that it can preheat up to 129 degrees. Once that's ready, I'll place the product into the machine, pressing start again so the temperature can start rising, and I'll look through the microscope to see exactly when the crystals start to melt. And nothing happened for a while, but the crystals look like they started melting at 132.8 degrees Celsius and were completely finished melting at 133.6 degrees Celsius. So that'll be the melting point range for this product. To run the IR spec, I'll place a small amount of the crystals onto a salt plate and then add a drop of Nugel, which is in this container here. And to make sure that only a small drop is added, I'll push all of the oil out of the Pasteur pipette, wiping it on the sides of the container so that only a little bit of residue is what's placed onto the salt plate. Then the two salt plates can be placed together, and I'll mold them until the product forms a film with the Nugel like shown here. That can now be placed into the spectrometer to see how the product turned out. And that turned out as expected. We can see the carbon-hydrogen bonds from Nugel, but we see the carbonyl peak around 1662, as well as the peak for the alkene around 1600, and we can also see some small aromatic overtones. Now I can weigh out the empty watch glass to get the weight of the product isolated. With the remaining product, I'm going to show how to do the recrystallization technique in the case that these crystals weren't pure. To do that, I'll move the crystals over to a Craig tube and place it in a hot water bath. Then in a separate test tube, I'll get some ethanol, which will be the recrystallization solvent, and also place that into the hot water bath. I'll start adding the ethanol slowly, making sure to stir the solution really well so that not too much solvent is added. I'll continue to do this, adding a little bit more solvent at a time and continuing to stir the solution just up until the product is fully dissolved in a minimal amount of ethanol. Once the product has been fully dissolved, I can remove the Craig tube from the hot water bath and place it in an ice bath to make sure that the product can come out of that solution. After a little bit of time and some stirring, we can see the product coming out of solution, so that's a good sign that the right amount of ethanol was used. I'll take it out of the ice bath now and place it back into the hot water bath to redissolve the solid back into the solution. Once that's done, I'll place the Craig tube on a test tube rack so that it can cool off slowly and recrystallize slowly at room temperature. It's kind of hard to see at first, but at the bottom the crystals are starting to form, and I actually sped this video up quite a bit. In reality, this process took probably about 20 to 25 minutes. Once the product has fully recrystallized, I'll scrape the sides of the glass with a spatula just so it's easier to remove the crystals. And to remove them, I'll place a stopper into the Craig tube and place both of those into a separate propylene test tube. I'll be placing this into a centrifuge, and while it runs, the solvent will be pulled to the bottom of the test tube while the stopper blocks the crystals, keeping them inside the Craig tube. And I'll want to equalize the weight with a separate propylene test tube filled with water. I'll place those two test tubes opposite to each other inside the centrifuge and let that run for a couple of minutes. We can now see the solvent at the bottom, so I'll just remove the Craig tube with the crystals inside. The crystals can be taken out and placed on a watch glass, and now we have pure crystals that we can characterize.